Okay. So the concept is weightlessness, mm, and I have weightlessness. Okay. So this concept of weightlessness is basically shows how the weight varies if you move throughout the earth, okay? Or if you basically move on the planet, on the earth mainly, okay? So let's imagine that I have the earth, okay? This is my earth, okay? And the earth is basically, okay. So the earth basically spins on its own axis, okay? So it usually spins like this. This is the axis, okay? So this is the earth's axis, okay? On which it spins, okay? We know that the earth is basically tilted on its own axis, right? But but for now we ignore the tiltness of the earth, okay? Now, um, okay, okay. So this is the rotation of the earth, okay? And this is how the earth moves, okay? Come on. Okay, this is how the earth moves, okay? Okay, this is how the earth spins, okay? Now, if we if we try to understand how fast the earth is moving, so let's first find out the values, okay, with which the earth is moving, okay? So we know that the mass of the earth is, sorry. So the mass of the earth is 6.00 exponent 24 kgs, okay? And its radius is 6.4 exponent 6 meters, okay? And the time the earth required to complete one of its motion is basically 1 day, okay? Or you can just convert 1 day afterwards, okay? So these are the three things, okay? So we are considering the spinning motion of the earth, okay? Mm, okay, the spinning motion, okay? So these are the three data that we have, right? Now, if you look the earth side view from the sideways, okay, basically we also know that this is the equator of the earth, okay? Okay, the horizontal line cutting the earth, okay, so this is the equator of the earth, okay? Equator, and we have the vertical lines, and this vertical line is basically the axis, okay? Both are the imaginary line, okay? One cuts the earth vertically and the other cuts the earth horizontally, right? And both are the imaginary lines, okay? So this is the axis, by the way. So this is the axis, okay? And that is the equator, okay? Now, earth is basically moving around its axis, right? So the side view looks like this. If I draw the side view here, Okay, so the side view looks like this. Okay, the Earth is moving like this. Okay, so it is moving like this. Okay, and this is the axis, and let's say this is the equator. Okay, I cut the Earth from the equator. Okay, so if we try, this is by the way the circular motion. Okay, if let's say one object is right here. Okay, if one object is right here, so this object will basically going to perform the circular motion. Okay, and one of its circular motion is going to complete in one day, right? One of its circular motion or one of its rotation will going to complete in one day, right? This is what we are
Yeah.
talking about, right? Now if we try to find out like how much speed with which this particle is moving, so we can find that out. Okay, this is by the way the motion. Sorry. Mm, 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 mm. So this is by the way the motion, right? Now if we try to find out how much fast the earth is moving, so we can do speed is equals to distance over time. Okay, speed is equals to distance over time for this particle, right? And since you can see that this particle is basically completing the circumference of the circle. Okay, and we know that the circumference of the circle is going to be 2 pi r, right? So 2 pi, and the is basically 6.4 exponent 6. Okay, divided by the time is 1 day, which mean 1 day contain 24 hour, 1 hour contains 60 minute, 1 minute contains 60 second. Okay, and this is going to be the velocity, right? So can you find out the velocity for me, please? Yes.
It is 4.65 into 10 to the power 20.
Mm, bro, how? It shouldn't be that much. It should be just hundreds. I'm getting 65, 465. Are you getting? 465.
Yeah, yeah, yeah. I'm getting this. I think I put 10 to the power 24 instead because I saw
Oh,
mass and I thought that was.
no, the radius. We have to put the radius,
Yeah,
okay?
yeah, yeah. Yeah, yeah,
Hmm.
I got it.
Now, the object is moving with this much of speed, right? And the Earth, the whole Earth is basically moving around its own axis with that much speed, right? But since the Earth is moving with a constant speed, so we cannot feel any motion, okay? Like in the plane, if you sit in the plane and the plane is like moving with a constant speed, so you don't feel its motion. But if it's accelerating or if it enter in a turbulent zone, okay, so you can see the effect, you can see the motion, or you can experience the motion. Or if it takes the turn, then you can experience the motion, right? Now, so we can say that um, due to the constant motion, okay, due to the constant motion, wait, I have to take this thing up. The constant motion, due to the constant motion, we can't we can't feel anything, right? So due to this is due to the constant motion, right? Now, if the earth is spinning with this speed, okay, so obviously the object will going to experience some sort of centripetal force because it is completing the circular motion, right? So we can say that actually, so since the object, come on, since the object is under the circular motion, okay, so we can say that, so it will experience the resultant force, okay. Okay, so this is the first thing. Now let's talk about the resultant force. Okay, can you tell me at which point there will be maximum resultant force? What do you think? Will the resultant force be maximum at the axis or at the pole? Yes, what do you think?
Uh,
The axis is basically,
Resultant force.
yep, the axis is right here, and the axis is here, and the equator is here, right?
Or at the poles.
Okay,
Mm,
imagine the fan is moving, right? At which
yeah.
point will you put the finger, if you're putting the finger, so at which point would you put the finger so the effect will be maximum? Will it be at its wings, or will it be in the center? Yes.
Uh,
So imagine we have a fan. Wait. uh what, bro? Sorry, my pen stopped. So just a second. Okay, now, so just imagine yourself, okay, this is the fan, okay, okay, and okay, this is the fan. So if you, let's say somebody puts the finger in, okay, so if someone put the finger here, so will it feel something, or if somebody puts the finger here, will it feel something? Okay, which one gets hurt more than the other one?
the one close to the blades.
Close to the plate, okay. So which means if somebody put the finger here, so it will going to be hurt, okay. But if somebody puts the finger here, it won't affect anything. It won't get affected by anything, right? Even if you put the finger right in the center, then you will only, then you will feel minimum motion, okay, clear?
Yeah.
So similarly, the effect of the circular motion at the pole is minimum than the effect of the circular motion at the equator, right? Clear? Is that clear?
Yeah.
So the effect of circular motion is minimum at the poles, or at the axis, okay, then at the equator, okay. So you can say that the resultant force will also be at the equator, okay, and it will be greater than at the pole, at the right. Is this concept clear?
Yeah.
Hmm. Now let's try to find out the value of the weight on both of the cases. Okay. So if I have the earth right here, okay, and a person is standing right here on the surface of the earth, right? And its weight is, its mass is, the mass is given, the mass of the person, let's say 70 kg. Okay. Now, if I, okay, so if I put in the value, if I just draw the forces here, so the forces will be the weight, okay, and the normal reaction force. The weight will always act from the center of the body, okay, and the normal reaction force, okay. This is the normal reaction force and this is the weight, right? And please keep in mind the weight of your body, the weight that you feel of your body is basically due to the normal reaction force, okay. It is not due to the actual weight, okay. Because if you if you like start walking on the water, you will fall, right? Because the earth attracts you, right? Similarly, if you try to jump, okay, so during the jump you don't feel any weight, right? You're like moving weightless, right? Because you're not in contact with any other thing, right? But as you make contact with the ground or something, then you will feel how weighted you are, right? So basically the normal reaction force is the one causes the weight, okay, or experiences the weight, okay. So I have this contact force causes the weight, okay. This is the first thing, right? Contact force causes the or causes the sensation of the weight, okay. Sensation of the weight, right? So okay, now, so if you lose any contact from the earth, you won't feel any weight, okay. Now if we try to find out the weight at the pole, okay, for the person, okay, so it will going to be um weight is equals to mass, which is 70 times 9.81, which is the gravity, right? So it will going to be how much?
687.7. 686.7.
6.7. Okay, fine. Now if we bring the man on the equator, okay, we bring the same man on the equator, so yeah, so now the equator is right here, the equator is right here, okay, and this is your man, right? Now if you are trying to find out his weight, so for this case, the weight is acting in this direction. Okay, the normal reaction force acting in this direction, right? Normal reaction force and weight. But due to the circular motion, there will be resultant force, right? So in this case, we can say that for this case, we can say that the weight is basically equal to normal reaction force, and then we can find it out, right? But for this one, we cannot say that the weight is just equal to the normal reaction force. We can rather say that weight, mm, weight minus the contact force is equals to the resultant force, okay? And the resultant force is basically mv square over r, okay, or mi omega square. We can use anything, right? Okay, but I'm using mv square over r because it's a general, it is a like actual form, right? And mr omega square is the derived one, okay? Now, the weight is what we found out, okay? We can put that in, right? So it will get 686.7 minus the mass of the man is 70, okay? The speed is uh, 463 or 465 divided by the radius of the earth is going to be 6.4x minus 6. You have to square it. Okay, this will give you n. Okay, and n is basically the sensation of the weight, right? So can you find the weight, please?
686.7 again. 7.
It shouldn't be that value.
Huh?
It shouldn't be. It should be smaller than that. Mm, we are doing 0.7.
Oh, oh.
What?
684.
What did you do? You didn't put the square, right?
I I didn't put the square. Yeah.
Mm, okay. So n become 684.7, right? Or something.
684.3.
3. Okay. Newton. Okay. Now this is your feel like weight. Okay. And basically the weight decreases. Okay, the weight decreases, right? A bit, right? So the same person is moving from this point to this point, okay, and its weight is basically decreased by 2 Newton, right? So this is basically the weightlessness, okay? So if you move throughout the earth, okay, so due to the tiltness of the earth, sorry, due to the motion of the earth, your weight is basically become lesser than what how much you are, right? Is that clear? And this is
Wait, so that
basically,
means.
mhm, yes.
Wait, so if you're wait, if you're traveling somewhere,
Mm-hmm.
your weight will change.
Yes. But it depends if you travel from the equator to the poles, okay? So if you're living any country that are near the poles or near the equators, okay? Near the equator or near the poles, okay? So when you move to one country to another country, so your weight will be changed from like by 2 kgs, okay? By 2 Newton.
It'll in- it'll increase when you go to the equator.
Yes. It will decrease basically. Like
Decrease.
at equator, it will be lesser.
Okay.
Okay. So, and at the poles, it will be greater.
Is that because there's a greater attraction at the poles?
No, it is because we have the greater effect of the circular motion. Okay, because the attraction remains the same throughout the Earth, right? But the circular motion, the spin of the Earth is more active in this region and least active in this region, right? So that's why. Okay.
Okay. Yeah.
Hmm. Now, so this is basically the concept of the weightlessness. Okay. Now you can feel the similar effect in on the lifts. Okay, if you take the bathroom scale with you on the lift, okay, and just put the scale the weighing machine, okay, and then stand on it and move down, okay, in the lift, so your weight will decrease by 2 kgs, okay, when the lift goes down, approximately 2 kgs, okay, and when you move up, the weight will increase by 2 kg, okay, and that's why sometimes you feel heavy when you are moving upward in the lift. Maybe you experience that.
Okay.
Now, so this is the simple concept of the weightlessness, okay. Now, if we move on to the other thing, or shall we just do the question? Wait, I have this question. Okay, this is one question. Okay, the weightlessness concept. I have this question. Okay, we can consider this one. Okay, let me just try this one and that one. And do I have any other? We did that one. Angular velocity omega, and if anything, nope, I don't have. So Earth determine the requirement in the circular motion. Okay, trying this one. Okay, the reading. This is the sensation of the weightlessness, but okay, let's try. These are the two questions. Okay, copy and paste. Mm-hmm. Paste the pages. Okay, let's. Okay, can you please read the question?
A spherical planet has mass m and radius r. The planet may be assumed to be isolated in space and have its mass concentrated at its center. The planet spins on its axis with angular speed omega, as illustrated in figure 1.1.
So okay.
A small object of mass m rests on the equator of the planet. The surface of the planet exerts a normal reaction force on the mass. State formulae in terms of m, capital M, small m, r, and omega for the gravitational force between the planet and the object.
Okay, so you can say that mm, GMM over R square, right? This is the gravitational force, right? Clear? So let me see
Yeah.
which question is it. Done. Okay. Now, yes. So this is the second thing. Okay, move on, please.
The centripetal force required for circular motion of the small mass.
Hmm. Okay. Okay. Basically, they have given us the omega, so we have to write in term of omega. Okay. Hmm.
The normal reaction exerted by the planet on the Mars.
Okay. So now you know that if you recall this concept, so you know that you have to make this equation, right? And this equation can relate the contact force. Okay. So to make the contact force a subject, I can write this as mm, weight minus the centripetal force. Okay, and weight is basically given in the form of gmm over r squared minus m r omega squared. Is that clear?
Yeah.
Okay, good. Okay, let's move on.
Wait, what is this GMM? Isn't it
The
supposed to be weight?
No, the weight is basically like for the gravitational force. In this case, you have to use the weight. Like you have to use the formula of gmm over r squared for the weight, right? Because in previous classes and in AS level, we use the weight as mg, right?
Yeah.
But in G, we derive the equation that G is given by gm over r squared, right? So if you put the value of G in it, so you'll get the value, you'll get the weight formula, right? Clear?
Oh, okay.
So in A levels, you're not allowed to use the gravity, right? G as 9.81, right? Because it changes according to the distance, right? Or as the distance changes, right? So that's why. Clear?
Yeah.
Now, so if I have, so that's why this is the weight and that is a normal reaction. That is a centripetal force. Okay, so move on.
Explain why the normal reaction on the Mars will have different values at the equator and at the poles.
Hmm.
That's because the at the equator the object will be undergoing circular motion, but not at the
Okay,
poles.
actually the opposite.
Um, wait,
Okay,
circular motion at the poles?
no, circular motion at the equator.
I think. Wait, didn't I say that?
I think you said the opposite, or I think you said the axis and poles. Axis and pole are the same thing, okay? The equator is a different thing, right? But fine, fine. Okay, so you have to say, um, due to the spin motion of the Earth, okay, due to the spin motion of the Earth, um, the contact force, to explain why, and contact force will be lesser at the equator than at the pole, okay? Okay, now please move on.
The radius of the planet is 6.4 into 10 to the power 6 meter. It completes one revolution in 8.6 into 10 to the power 4 seconds. Calculate the magnitude of the centripetal acceleration at the equator.
Okay, so for the centripetal acceleration, we can say that, mm, okay, and
We can take the
yes,
what's this?
the R
The
omega
2
thing.
pi r, 2 pi r
For
circumference, no, it's distance.
no, you don't have to. Basically, the formula that you're using will automatically give you the centripetal acceleration. If you are finding the speed, then you have to pick that thing. Okay. Okay. So I'm using the r omega square formula. Okay, and the r is 6.4. Okay, exponent 6, and you know that omega is 2 pi over t right? So 2 pi over the value of t is basically 8.6 exponent 4 square. Right now, can you please calculate the value?
Yeah. But we can do the other method, right? We'll still get the same answer.
Yep.
As in, okay.
Like if you're using the 2 pi, then like you won't get the actual thing because you won't get to the actual thing because they're asking for the acceleration, okay? And using that method, you will end up getting the speed. That's it. So that's why. And it will be like very long way, okay? Not recommended.
Okay. I'm getting 0.034.
Okay, 3, 4. Okay. So this is the centripetal acceleration, okay? Okay, on the poles. Since on the pole, the resultant, the centripetal force is basically zero, right? And the effect of the circular motion will be zero. So the acceleration will also be zero, right? Okay. Now,
Wait, why
please,
is it 0?
because on the poles, okay, the effect of the centripetal motion or the effect of the circular motion will be negligible or zero, right? So that is why. Clear?
Okay.
Because the thing the everything is spins from the same point, okay, and that same point doesn't have any motion, right? But the points around that point will have the motion, right? Like if you spin the ball, so if and hold one point and spin the ball around that point, okay, so that one point remains the same, okay, it won't move, okay, but the points around it will spin, okay. Clear? Now, so suggest two factor that could, in case of the real planet, causes the variation in the acceleration of the free fall of the surface. Mm-hmm. Yes. What do you think?
That is changes the small g value, right?
Yes. You can say that. The planets that are nearby, okay, so their gravity change our gravity, okay. So, um, the sorry, um, the gravity change the g, okay, the acceleration of the free fall, right? And the second thing is, um you can say that the density is not uniform throughout the planet, okay? So where the density is greater, the effect of the gravitational field will be larger, and where the density is smaller, like in the sea, the effect of the gravitational field will be smaller, right? So the the density is not uniform, right? Yep, that's it. Okay, now.
Does,
Mhm.
uh, for the Earth, the density is uniform, right?
Actually, for the Earth, in reality, the density is not uniform, right? Because we have more water than the sand or than the land. So in the portion where we have the land, the density is greater, and in the portion where we don't have the land, or the water or the gases, the density going to be smaller, right? But we assume in this chapter that the density is uniform throughout the planet. Okay, this is the assumption. Okay, but they're talking about the real planet. Okay, clear?
Okay.
Okay, now okay. Okay, try this one.
The Earth may be considered to be a uniform sphere of radius 6.37 into 10 to the power 3 kilometers, with its mass of 5.98 into 10 to the power 24 kg, concentrated at its center. The Earth spins on its axis with the period of 24 hours. Calculate using Newton's law of gravitation the gravitational force on the stone.
Okay, you can use F is equals to GMM over r square, because this is what the Newton's law of gravitation. Okay, and they're saying that this is the object that you have, and this is the equator. Okay, and at the equator there is a mass of 2.5 kgs. Okay, so six, you just put the value of 6.67 exponent negative 11. Okay, and then m is going to be 5.98 exponent 24, or 2.5. Okay, these are the mass values. Okay, now the radius, the separation is going to be the radius, which is 6.37 exponent 3, and then we have the kilometer, so I have to convert it into meter. So 6. Okay, and you have to square it. So just solve it, please. Yes, how much?
1 second. 24.57.
24 point 24.57. Fine. Please move on.
Determine the force required to maintain the stone in its circular path. The centripetal force.
Determine the force. Yes, you have to. Okay. So F is equals to m r omega square, or we can use that value, this value. So the mass is going to be 2.5. Okay. The radius is going to be 6.37, 6.37 exponent, 6, and the time is 24 hour. Okay, and 1 hour contains 60 minutes, 1 minute contains 60 seconds. Okay, and you have to wait, sorry, my bad. 2 pi over 24 into 60 into 60, and you have to square it, right? How much?
1 second. 0.084.
Okay, 0.084. Okay, now, okay. So you have the Newton meter, and the Newton meter is going to read the meter reading, right? And you know that the Newton meter is okay. So if you have the Newton meter, so yeah, and let's say you're hanging something with the Newton meter right here, okay? So Newton meter is basically show the mass of what you hang due to this force, okay? Due to this force, right? Now the weight is acting downward. The weight is acting downward, right? And we have, this is the weight, okay, and the centripetal force, okay, the tension in the spring of the Newton meter is acting upward, okay, and the weight, okay, the weight minus the tension gives me the centripetal force, okay. Okay, so is give me the centripetal force, okay, which is basically the resultant force. Don't write this way, okay, just put the value, okay. So weight is basically how much? To 24.57 minus T is equals to the centripetal force 0.084, right? And then if you subtract the values, so 24.57 minus 0.084 is equals to T, right? So this gives you the tension in the Newton meter that basically gives you the value, right? So just find that out.
It is 24.486.
Okay, 24.48. Okay. So by the way, there's a satellite motion transition of the waiter caused by the contact forces from his surrounding. The astronaut report this as a weightless, despite being the gravitational field. State what is meant by the um. Okay, so now what will you say this, or how will you answer this?
Mm,
Okay, let's say. By the way, we didn't discover this thing yet, but let me just explain to you. So this is the Earth, okay, and let's say this is the satellite, okay. And in the satellite, we have a person, okay, and that person reports the weightlessness, okay. Now, the gravitational force is actually toward the center of the Earth, provides the centripetal force, right? Okay, now, so if we say, okay, and this is the contact force, okay, and the contact force arises when the person makes contact with the floor of the satellite, right? So if the weight become equal with the normal reaction force, then the contact force will going to be zero, right? Right? Is that clear? Are
yeah.
you getting? So look, this this satellite performing the circular motion, right? This is the weight, this is the normal reaction force, and that is the centripetal force, right? FC, right? We know that weight is basically providing the centripetal force. Contact force opposes the centripetal force is equals to MA or MV square over R. Okay, or you can just say FC, right? So if this value and that value become equal, okay, if these two values become equal, then N goes to zero, right? And we know that,
Uh, is this
yes,
basically the uh, I think it's first chapter where like the radius or separation is equals to like arc length. I think I don't know.
no, not related to that much, or not related to that thing. Okay, it's just a concept where if we say if we go away from the planet uh to that much distance where the centripetal force and the weight become equal, okay, then the contact force goes to zero, right? And due to the fact that we experiences our weight due to the contact forces, right? So that is why since the contact force is zero, so it feels the weightless. He feels the weightlessness. Okay, clear? So we
Wait.
can. Mhm.
So basically, if the weight is zero, that means contact force is zero.
No, weight is not zero. Weight is equal to the resultant force. Okay, let me just write the value or write the things. Okay, so gravitational force provide the centripetal force to the satellite. Okay, this is the first thing. And okay, now when the gravitational force become equal to the value of centripetal force, centripetal force, the contact force becomes zero, right? Because if this and this have the same value, they both get cancelled out and n goes to zero, right? And we know that n is basically what causes the weight sensation, okay? Since n causes the sensation of weight, okay? So the weight will be zero as well, right? Like the weight that he is experiencing is zero, right?
So
And
he
this is
feels.
nothing. Like
So he
he
feels
does.
like
Hmm.
he just floats around, right?
Yes,
That
yes,
means.
yes, yes.
So
So
that's how he can float in space.
yes, may not in the space, but in actually he is in the space, but he is in the gravitational field. Okay, so if you overcome the gravitational field, then you have the space with no gravity, so you float. Okay, but if you are in the space and you are moving in the circular motion around the planet, okay, but uh, due to the fact that you are far from the planet, so the weight that is acting on you will be lesser, okay, and contact force will goes off, and that's why you float. Okay, this is the concept. Clear?
Yeah.
Okay, so that's it. So this is the one concept. Now we'll do the two remaining concept in tomorrow's class, and then we'll be done. The first portion of the chapter will be done. Okay, we'll then move on to the next portion. Okay, so that's it.
Okay.
Okay, take care, bro. Love face.
I love this.
Love face.